Hello, everybody. Welcome to your next lecture. This one is on earthquakes. You're going to have two lectures on earthquakes. This is the first one, and we're going to be going over some of the kind of theory behind how earthquakes happen, maybe going over a little bit of historical earthquakes. Next time, we're going to go over mostly earthquake hazards. So today, we're doing mostly just kind of theory behind how earthquakes occur, why they happen. So I start off with this picture. This is a very famous earthquake, most destructive earthquake in America, actually, in American history, I should say. San Francisco, 1906. It's really the earthquake that started a lot of seismology, the science of seismology. So it was a very devastating earthquake. We'll talk more about that later. But one of the most devastating, actually the most devastating earthquake in American history. So more about historical earthquakes later. But I do kind of want to talk about causes of earthquakes. So, most earthquakes are just naturally produced by things like tectonic plates moving. Though this is an earthquake scarp. I showed you some pictures of scarps in the last lecture. So scarps are those kind of the scar that's left on the earth after the fault has moved during an earthquake. Okay, so this, you can see this fault block here moved up. This one moved down, and this is the fault plane right here that I'm scribbling on. Okay, so anyway, that's a fault scarp. So most of them are natural; they occur from tectonic activity. However, other things can cause earthquakes too. Volcanoes can cause earthquakes, and earthquakes can cause volcanoes too. So we see that very prominently in the Mount St. Helens disaster in 1980. There's also some human-induced earthquakes. So, for example, you can induce earthquakes by the pressurized pumping of fracking fluid, lubricates fault planes and allows them to slip a little bit more easily. So there have been human-induced earthquakes from fracking. We'll talk more about that in the next lecture. And there's also earthquakes can also be generated. This is a picture of, I can't remember which it was, Kim Jong-il or one of the North Korean dictators. But you could also generate earthquakes, by the way, by detonating nuclear bombs underground. So that's another way. Actually, that's how we know and we monitor a nuclear bomb testing over the globe is from the seismic waves that they generate. So those are some of the ways that earthquakes are caused. But I want to talk specifically about what is an earthquake and how do they come about, and et cetera, et cetera. So earthquakes. First of all, what is an earthquake? It's ground shaking. Okay, ground shaking. This is question number one. Caused by seismic waves or from seismic waves. Okay, seismic waves are really just big mechanical waves. Okay, they're mechanical. So they're waves that are propagated through material. And you might say, like, well, what kind of wave isn't propagated through material? Light waves. Light waves, any kind of radiation, radio waves, microwaves, whatever, those do not propagate through a material. They can propagate through outer space, right? They can propagate through empty space, whereas mechanical waves are different. They're propagated through a material, whether it's gas or liquid or matter or whatever. But seismic waves are just big mechanical waves that are propagating through a solid, right? Through the earth. So that's all a seismic wave is. It's literally the same kind of thing as a sound wave, actually. So it's a big mechanical wave. You could almost think of it as a sound wave. Of course, you can't hear it because the frequency is not the kind of frequency that you would be able to detect audibly. But it is ultimately just a sound wave, a big mechanical wave. So anyway, tectonics are the main cause of plate tectonic motions are the main cause of earthquakes. So you might remember from the tectonics lecture that most earthquakes occur near the plate tectonic boundaries. So tectonic earthquakes involve frictional sliding along a planar surface. So that planar surface is the fault plane. Earthquakes occur when the stress on the fault plane exceeds the frictional strength of the fault plane contact. Let me say that one more time. It's very, very important. Earthquakes occur when the stress on the fault plane exceeds the frictional strength of the fault plane contact. So earthquakes happen basically when so much tectonic stress builds up that it overcomes the friction on the planes. So I'll get a little thing to demonstrate this to you. So if I get two books like this, right, you could think of these as like the two different fault blocks, right? And the plane between them, so the surface right here would be the fault plane, right? And then here's another fault block that's on top of it. So, you know, the fault blocks aren't going to move past each other because there's friction, right? So right now I can kind of tilt these a little bit and they won't move because there's friction between the two books, right? But if the stress builds up enough, right, you can finally get movement because the stress, the tectonic stress, overcomes the frictional strength on the fault plane. Okay, so it's a give and take between tectonic stress and the frictional strength of the fault plane. So faults happen. They are all over the world. Even here in Texas and Corpus Christi, where there might not be earthquakes, there's always faults. They're everywhere. They're ubiquitous. It's just that those faults might be active or inactive. But the faults are already there. The Earth is filled with faults. So the problem isn't faults. It's that there has to be enough tectonic stress to overcome the frictional strength along the fault planes. Okay? So there's the fault plane right there. Oh, whoops, my pen isn't on again. I turned on my pen. So there's the fault plane right there. Okay? And here's the hanging wall block, footwall block. We talked about that in the last lecture. So when, again, the tectonic strength tectonic stress overcomes the frictional strength, then you're going to get movement, and that's going to generate the seismic waves. So earthquakes are secular, and a lot of the science of understanding the cyclical nature of earthquakes emerged after this very famous San Francisco earthquake, April 18th, 1906. Very, very famous earthquake. Destroyed. You can see the headlines here. City wiped out. City is doomed. Loss is, $200 million, which was a lot of money back then. And San Francisco emergency edition. Right, this is just a devastating earthquake. You see large parts of the city were ravaged and razed by the earthquake. A lot of people, of course, wanted to understand why did this happen. Will it happen again? Where do earthquakes happen? They wanted to know, is this going to happen again? That was the main question plaguing people's minds after the 1906 San Francisco earthquake, right? So there was a gentleman who set out by USGS, Harry Reid, who was given the task of understanding this earthquake and predicting, is it going to happen again? Is it going to occur again? Do we need to relocate this city, or should we rebuild it, or what should we do? So Harry Reid went out all around the surrounding area of San Francisco, and what he found, because of course at this time people didn't know hardly anything about earthquakes and what causes earthquakes, but what he saw was a lot of this: fences broken, displacements occurring. Right? Remember we learned in the last lecture this is called a displacement, right? Offset. Okay, you can see this even today, right? They didn't build this. Isn't that amazing? They didn't build that fence like that, right? It's just been displaced that much by different earthquakes. So he went around and he found that all these fence lines were broken. Okay, there are all these fault scarps and things, and it showed that the Earth is moving. Okay, now maybe that seems obvious to you now, but it wasn't obvious at that time. Earth was moving, the crust was moving, and that's what's generating the shaking. Okay, so the main idea that emerged here was something called elastic rebound theory. So elastic rebound theory goes like this. It's a cyclical theory. So first you start off with two fault blocks and a fault between them. Okay, it's the original position. The next thing is tectonic stress begins to build up. And as it builds up, it starts to elastically deform the surface. Let me give you an example. If I take this is just a plastic fork that I happen to have here. I'm going to elastically deform this, and when I elastically deform, you can see that I can bend the fork, but it'll pop back up if I let go, right? That's elastic deformation. Elastic deformation is when you change the shape, but it will snap back once you release the stress. Plastic deformation is different. Plastic deformation, think more of like Play-Doh or something like that. Once you change the shape of Play-Doh, it's not going to snap back to its original shape, right? That's plastic deformation. Elastic is different. After you take that, and you probably know like an elastic band, right? If you stretch an elastic band, it'll snap back to its original position. Well, that's the way the Earth is. The Earth is elastic. So after the tectonic stress builds up, the Earth kind of bends. So I'm hoping you can see there in the lecture. Of course, I guess you look at it when you're looking at it, it's up there. But you kind of see how the Earth is. Whoops! You can kind of see how the Earth is bending here, right? Do you see this? Where's my? Whoops! Like this. Yeah. See how the Earth is kind of bending right there? That's the elastic energy building up within the crust. Finally, though, what happens is that the tectonic stress and the elastic energy build up so much that it overcomes the frictional strength. And then when it overcomes the frictional strength, boom, it snaps. And the elastic energy that is built up is released, and it rebounds, right? The Earth rebounds and returns to its original shape. And that's why it's called elastic rebound theory. So that is the main theory that explains how seismic waves are generated in the Earth, how earthquakes are generated. Okay, so the reason that they're cyclical is that after it snaps back to its original shape, what happens? It starts to build up again. Elastic energy starts building up again as tectonic stresses build again. So what I want you to understand about elastic rebound theory is that there's a build up, release, build up, release, build up, release. And every time there's a release, there's an earthquake. Okay, so that's how earthquakes work. So I've described now number 1, 2, 3, 4. Where do earthquakes generally occur? Right, we've talked about this quite a lot. Where earthquakes generally occur, they occur near tectonic boundaries, plate tectonic boundaries, because you need the tectonic stress to create the earthquake. All right, just an interesting example here. UC Berkeley, which is right outside of San Francisco, they built the stadium right on the San Andreas Fault, so you could actually see places where the stadium is coming undone. So it wasn't a great place to build it. I don't know. Maybe that's why they don't have a great football team. But anyway, Hollister, California, you can see the deformation building up right in their fence line there. So anyway, you could literally see the deformation building up, right? And it hasn't offset yet. It hasn't snapped yet, but it will snap someday. Here's a really interesting example from Imperial Valley, California. This is deep South California. This is like near the Mexican border. You could see the rows of agricultural rows offset, right? So offset of 2 feet there. Here's an offset of 400 feet. Wallace Creek in outside of San Francisco. So you can see this amazing. I've shown this picture quite a bit. But this amazing offset in the creek there. So it's 400 feet it's moved since that creek has been established and since it started flowing, and pretty amazing. So again, remember that earthquakes happen where? They happen on plate tectonic boundaries. So plate tectonics, right? The whole theory went over already of how the convection in the mantle is moving the plates along the surface. Every time there's a sudden movement, it creates that earthquake. And of course it creates it along the tectonic boundary. So here again is a map of all the magnitude 5 earthquakes that have occurred since 1960, or higher than magnitude 4. I'm sorry, that was magnitude 5. Higher than magnitude 4. Magnitude 4 is kind of the earthquake that maybe it's big enough to actually feel. You could probably feel smaller ones than that, but they're earthquakes that you would take note of. You can see there's thousands and thousands and thousands of them that have happened since 1960. There's actually a magnitude 5 earthquake somewhere in the world every day. So there's a magnitude 5 somewhere. So anyway, In the pre-digital era, we had these very primitive seismometers, seismographs, and you had a needle that was on a pendulum, and as the ground shook beneath the pendulum, of course, stayed put and recorded the shaking generated by the earthquakes, right? Of course, now we have very sophisticated things that can digitally record that, and we even have stations that are just solar powered, and we can put them all over, even in the open ocean, in Antarctica or wherever, that can, I shouldn't say open ocean, but out in the middle of the Pacific Islands somewhere. But anyway, we can have a huge net of interconnected seismograph stations, all talking to each other and all in communication with each other, so that when an earthquake occurs, a tremendous amount of information is known about it now within seconds. And I mean within seconds. These are all interconnected. They all kind of communicate with each other on a network. And within a second of when an earthquake occurs, lots of information. We know exactly where it is, how deep it was, and where the seismic waves are headed towards. And so actually, with the famous 2011 earthquake in Fukushima, remember the Fukushima power plant disaster in Japan and the tsunamis that occurred there, they were actually able to give those people about 20 seconds of pre-warning to get out of whatever building they're in, or hide or duck and cover, whatever it was. Gave them some warning to actually 20 seconds, which doesn't sound like very much, but seismic waves move very fast. But it was given enough time to maybe get out of the building and things like that. So anyway, that's all thanks to this tremendous IRIS-USGS network, the global seismographic network. And it's saves lives, so it's a big deal. Anyway, talking a little bit more about specifics about seismic waves now. There are a lot of different kinds of seismic waves. We'll talk about a few types, but main types I want to talk about are called P waves and S waves. P waves and S waves. So let me discuss a little bit about that. So P wave, that P stands for primary. Okay, so it's the primary wave. The S here, the S wave, stands for secondary. Okay, so secondary. That's the S wave. So the P wave is a faster wave. It's called primary because it arrives at a seismograph station primary first. It arrives there faster because it moves more quickly, right? It moves faster. So these go about 6 kilometers through the crust. Whoops. Gosh, I keep messing this up. Here we go. These go about 6 kilometers per second through the crust. 6 kilometers a second. Imagine that. That's really fast. Really fast. Okay, that's why you don't have much time in terms of warning for earthquakes, right? So you imagine if an earthquake is 100 kilometers away, you only have maybe 17 seconds or so to get ready. So move 6 kilometers per second. So anyway, S waves are different. S waves are the secondary wave. They are slower wave. They arrive second because they are slower. They only move 4 kilometers per second. Okay. Now, if we know exactly how fast a P wave goes, and we know exactly how fast an S wave goes, that means we know how far away the earthquake is. So imagine this. Let's say you know exactly how fast a car is going, okay? And you know that the car arrived, it took the car, let's say, the car is going 60 miles per hour, and we know that it drove for an hour. How far did it go? It went 60 miles, right? So if we know how fast the wave travels, and we know how long it took, then we know exactly how far away that wave was generated at. So we can actually figure out how far away the epicenter of an earthquake is based off a seismograph. So the way that we figure that out is we see the P wave arrival time, okay? And we see the S wave arrival time. So we can figure out from the P minus S wave, so P minus S arrival time, we can figure out how far away the earthquake is, okay? So you could see that what you'd have to do is measure the distance from the P wave arrival time and the S wave arrival time, and you take that distance and you compare it to the scale bar down here, and you can figure out exactly how far away your earthquake is. Now here's the thing. If you only know how far away your earthquake is from one seismographic station, it could be anywhere along a circle, right? We only know, like, for example, like it's 1,500 kilometers away. Now, if we get another seismographic station, and then we know it's 5,600 kilometers away, you'll notice that it could be at two different points. This point right here that I drew, or this point right there. So we need a third station to figure out exactly which of those points the epicenter was at. Okay, so we need at least 3 stations to figure out where an epicenter of an earthquake occurred. Okay. So anyway, here's again, world seismicity delineates those plate tectonic boundaries, shows where the boundaries are. One thing I wanted to point out to you is that there are a lot of earthquakes happening on plate tectonic boundaries, especially subduction zones. Subduction zones have the deepest and strongest earthquakes. All of the big earthquakes that have happened in human history, which, of course, when I say human history, I shouldn't say human history, but seismographic history, where we actually have good seismographs measuring these earthquakes. It's only for the last 100 years. All the big earthquakes, like magnitude 9 earthquakes, happen at subduction zones. The only one that hasn't had one yet is here in the Pacific Northwest. So a lot of seismologists predict that in maybe your lifetime or my lifetime, there's going to be a big earthquake there in Portland, Seattle, there in the Pacific Northwest coast. Okay, so get ready for that, because it could very well happen. One thing that's kind of cool is, like I said, there's just terrific monitors you can access on the internet now, and they just show you real time where the earthquakes are happening. And it's amazing because this thing is updated within seconds. An earthquake happens and we know about it within seconds. So you can see that wherever the earthquake's been occurring lately, you can see there's no earthquakes in Texas. But you see some in the Pacific Northwest just in the past. See, it's a yellow color right there. So we see that's in the past 2 weeks. Where are earthquakes happening today? Look at how many earthquakes we've had today, right? And look, all of these earthquakes that are in red, they're all bigger than size. They're all bigger than magnitude 4. It looks like maybe there's one magnitude 4 right there, but it looks like one. Few of them right here in the Andes. Okay, there's some out here. Some there, right? So we've had two in South America today. Pretty big earthquakes in South America today. Look how many there have been. Actually, this is very active. It usually is not this active. So there have been a lot of earthquakes today. It looks like a few magnitude 5s. Like I said, on average, there's only one magnitude 5 per day. So the fact that I'm looking at this and I can see at least 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, it seems like I'm seeing 10 times more than I'm used to. So this is pretty amazing, actually. So anyway, it's a really neat database. Shows you where earthquakes have been occurring. And another thing that's also really, whoops, I clicked on that again. Another thing that's also really cool is you can go to this thing. This is the global magnitude catalog of all. It's a catalog of all earthquakes. And you can put in your birthday here. So if you just put in, for example, I'll put in my birthday, right? So month is 9 and 17. Okay, and you go down there and search, and it'll show you all the earthquakes that happen. Now, see, like I said, there's only about one magnitude 5 earthquake. This is only going to be magnitude 5 and above. So normal is 1 magnitude 5 earthquake per day. So this is the magnitude. This MW number is your magnitude right here. So that's 5.7. So there was a 5.7 earthquake on the day I was born. So you can go on here and look up your birthday earthquake. Almost always there's at least 1 magnitude 5 earthquake on your birthday, and that was in I don't even know where that is. Halmahera. I wonder where Halmahera is. I'm kind of curious now. Okay, it's in okay, it's somewhere in the South Pacific Islands. Okay, off of Papua New Guinea. So there you go. Anyway, so that's kind of fun. Look up earthquakes on your birthday. So you can look up there's a huge global catalog of earthquakes you can look up. Moving on to Wadati-Benioff zones. So I asked a little bit about Wadati-Benioff zones, number 8. What are Wadati-Benioff zones? These are areas named after two scientists, named a Japanese scientist, Wadati, and an American scientist, Benioff. Wadati, Japanese are very interested in seismology for obvious reasons. There's a lot of earthquakes in Japan. So a lot of the seismological studies have been done by the Japanese. But anyway, Wadati-Benioff zones are areas where there are deep earthquakes. So they're basically subduction zones. And what we find is that as the subducting slab sinks into the earth, there's still earthquakes happening in it. There's still earthquakes. As long as it's lithospheric, there's still going to be earthquakes happening in that subducting lithospheric slab. When it heats up enough that it when it heats up enough, it's going to start to deform ductily instead of brittly, and then it will cease to have earthquakes. But until that occurs and it heats up enough, it has to go down 700 kilometers before that changes. So all the way down 700 kilometers. Isn't that amazing? We can still pick up earthquakes that deep. Okay, we can still pick up earthquakes that deep. And that should amaze you, because I don't know if you remember from the last lecture, but generally speaking, we don't get too many earthquakes generally deeper than 15 kilometers, because at 15 kilometers and below, we start to get ductile deformation instead of brittle deformation. So most earthquakes are happening above, rather shallowly. The reason that we can have really deep earthquakes in the Wadati-Benioff zones, or basically subduction zones, is because we have a subducting slab there, and it's going down all the way 700 kilometers deep. So it takes millions of years for that subducting slab to warm up hot enough to cease having earthquakes and to start behaving in a more ductile manner. All right, so we can actually figure out, besides P waves and S waves, I want to show you this. Besides P waves and S waves, we also have things called Rayleigh waves, which are surface waves. Another thing that's really cool that we can do is we can actually look very close at some of these seismograph stations and not seismograph stations, but seismographs, the actual, scratches on the wiggles on the paper. And we can actually pick up the echoes of the P wave in other places of the line. So in this case, it happens right here. There's actually the echo of the original P wave coming back. Because remember, this is just like a sound wave. It's a mechanical wave. So when we can actually pick up that echo, it tells us exactly how deep the earthquake was. So we can figure out how deep the earthquake was from the echo that we get. And we call that the P prime. And so you see there's a PP, which is the echo. Okay. But anyway, moving on. So those are the Wadati-Benioff zones of the world. Places where you see the red dots are places where you have earthquakes deeper than 500 kilometers. Very, very deep. You can see that the vast majority of earthquakes are happening at less than 35 kilometers. So those are all the black dots you see on there. So Wadati-Benioff zones are happening wherever you see the red. And those are places with deep earthquakes, which are mostly, as you could see, subduction zones, because all those places, right, this is the ring of fire that you see right here. These are all subduction zone earthquakes. Other places like this, you'll notice we get some blues and greens, and mostly those are happening because of the collisional process between the Indian subcontinent and Eurasia and the Tibetan Plateau. So those are deep mountain building earthquakes. But those also, subduction is going on in those places as well. It's just that it's a continent-continent convergence, but it still involves some degree of subduction. So anyway, like in the lower crust, because remember the crust there goes all the way down to 70 kilometers. Okay, it's very, very thick, deep crust. So anyway, let's talk a little bit about earthquake mechanisms. So you might remember we talked about faulting in the last lecture. These are normal faults, right? That's a normal fault. And those arise from extensional, pure shear extension. We get reverse faults or thrust faults. We could either get reverse or thrust from compression, right? Pure shear compression. Okay. So you might remember, sorry, I'm looking for my lecture assignment. What kind of faults are you going to see at convergent plate boundaries? You're going to get convergent plate boundaries. You're going to get pure shear compression. So you're going to get thrust or reverse faults. Extensional places where you get divergence, extension, tensile stresses, you're going to generate normal faults. And then transform boundaries are going to generate those strike slip kind of faults, right? So extension gives you normal, compression gives you reverse or thrust, depends upon the angle of the fault plane. And then horizontal sliding is going to come at transform boundaries along strike slip faults. Okay. So anyway, is crustal extension more typical of divergent boundaries or convergent boundaries? It's more typical of divergent boundaries. Okay. What kind of faults would you expect at subduction zones? Those are convergent boundaries. So you expect to find reverse or thrust faults at those kinds of places. Okay. So remember, wherever you get divergence, you expect to see extension, normal faults, normal type earthquakes. Okay. So kind of wondering what happens if I click here, see if this thing still works. Oh, it does. Okay. So here's a rift, just showing how a rift valley occurs. It's a pretty good animation. Okay. So that's how, just showing normal faults that and normal faults that are developing from an extensional regime, and how it's forming a rift valley there, because the crust is extending, it is pulling apart, it's thinning out a lot, and it's creating that rift valley, and that's what's gonna create the normal faulting. Okay. So a lot of that extension, I talked about basin and range in the last lecture. So a lot of that extension happened in Nevada, happened in the Southwest, just it resulted in the basin and range provinces there. And boy, it's kind of funny. This is what North America looked like about 20 million years ago. And once basin and range extension started about 20 million years ago on this southwest, part of our country, you could see it create a tremendous amount of extension out there. So it's kind of funny because look, Nevada hardly even existed back then. It was a teeny tiny skinny little state. So it got fat from the extension that's been going on in the what's called Horst and Graben basin and range type extension. So there's some examples. Again, right lateral strike slip fault there, and San Andreas fault in California. Here's some examples of Taiwan, 1999 Taiwan earthquake from a reverse fault. So you can see that this block dropping down, this block moving up, right, along a reverse fault. So compression always creates reverse or thrust faults. The largest earthquakes in the world, these are ones that happen at like magnitude 9 earthquakes that happen at subduction zones. So the way that this works is that as the subducting slab goes under the continent here, like let's say Japan, for instance, it starts to bend it back, right? It's bending it backwards, elastically building up energy, and then all of a sudden it will deform and snap back, and that's what generates the tsunami wave that are so devastating. Here's pictures of 2015 Nepal earthquake. That was a thrust fault earthquake. Happened in Tibet. Again, very devastating, magnitude 9 earthquake. We get a lot of those in a lot of earthquakes in the Himalayas and things, because there's that active compression coming from the Indian subcontinent running into Eurasia. Okay, so even the mountains here north of Los Angeles, they're created by compressional regimes there. So we even get mountain building going on right now in north of Los Angeles. So it's what creates the San Gabriel Mountains. It's really interesting because what's happening is there is a there's basically a step over in the San Andreas Fault. The San Andreas is, of course, a transform boundary. It's a strike slip, right lateral strike slip fault. But you might notice that here to the north of Los Angeles, it's more to the west, and then the San Andreas over here, south of Los Angeles, is more to the east. And so there's this portion of the San Andreas that's kind of a step over, and that creates a thrust or compressional regime right here, just to the very north of Los Angeles, going through. So there's a lot of thrust faults there in Los Angeles, which just creates a lot of the earthquakes, right? So most famous being a 1994 Northridge earthquake that I lived through. I mean, I went through that earthquake. I was there in Los Angeles at the time. I was only a 9-year-old boy, but I remember that earthquake very well. Okay, so there's transform boundaries, right? Transform faults. Where there a very prominent transform fault now? Well, the San Andreas. But there's a lot of transform faults that are right next to different sections of mid-ocean ridges. So, some parts of ridges will split, or some parts of the ridge actually spread more quickly than other parts. And when there's a unequal spreading rate, it creates a transform fault. So you'll notice that, like right here, you notice how there's this step over right here? That's a gosh, I hate how there's little things. I'm trying to draw this. Right here, you see that? I'm drawing a circle around that. That is a place where there's a transform fault because one part of the ridge is spreading more quickly than the other, and it creates it. So there's a lot of transform faults that connect different sections of mid-ocean ridges as well. So we call those parts in oceanography. We call those parts the little transform valleys. So anyway, let's see. San Andreas Fault is probably the most prominent example of a transform boundary, though. All right, so we went over what is an earthquake, right? And it has to do with earthquakes, of course, earthquakes are just ground shaking generated from seismic waves. But one of the most important things is that tectonic stress overcomes the frictional strength along the fault plane. Elastic rebound theory is the most prominent theory that explains how earthquakes occur. And how they occur is that tectonic stress starts building up. It elastically deforms the land surface. Okay, a lot of people think earthquakes happen when you start putting pressure and then the spoon breaks or the fork breaks. It's not the breaking; it's that it holds the elastic energy, and then suddenly, when there's slip along the fault plane, it snaps. Okay, that's what generates the earthquake actually. So those are cyclical because there's a build up and release, build up and release, build up and release from tectonic stress building up and being released along the fault planes. Where do earthquakes occur? They occur along plate tectonic boundaries, right? What are Wadati-Benioff zones? They're areas of very deep, very, very deep earthquakes, okay? It's places where mostly they're subduction zones or there are collisions occurring. So that's what you need to know for this lecture. We went by pretty fast. So anyway, I wish you a good day. We're going to continue with earthquakes in the next lecture. So thank you for listening, and I'll catch you next time.